This will be led, I believe, by Chung-Pei. Chung-Pei, are you ready to go?
Yes, I'm here. Can you hear me?
Yes, we can.
Great. Okay, so I have to confess that I had to teach just now, so I wasn't able to follow any of the 3 parallel sessions, but I have been in contact with the moderators of the 3 sessions, and then the 3 sessions were one about simulation of plasma physics, and 2 was about time domain physics, and then black hole shadows, number 2. Okay, so I think I'm just gonna kick off with a couple comments and thoughts from previous talks, and then I'll get Richard online to pass on to him to talk about the first parallel session. Okay, so I guess one thing I want to just follow up on was Michael's question at the end of Sasha's talk about jets and how Sasha had no problem launching beautiful jets and in fact had to work on killing it. And conversely, we heard at the end of Elliot's talk that, I think Ramesh commented on that was very difficult for them to even maintain any jet. And it appears that angular momentum or the condition of the infalling gas and so on, or the initial conditions, all of these are of crucial importance. So I guess my comment is, I presume people out there are doing a suite of simulations, perhaps varying this important quantity. So I would like to hear about that. And I guess a comment along this line is, this is very reminiscent of galaxy formation simulations, for which those are dear to my heart. And when you do isolated simulations, we got very different phenomena from the cosmological simulations or zoom in simulations in which we use realistic infall, baryonic infall prescriptions, or we use cosmological information and then examine how the infalling gas would affect the formation of disks and so on. Of course, it's very different physics here and there, different scales. But it reminded me of the different findings we had in that field. I guess just second quick comment is would like to hear from people is about, again, this is at the end of Elliot's talk, when he was commenting on the sort of extended fluid models for the prediction of the shadows and so on. I recall him saying that for the 2 temperature model that he was showing, he was astonished, also disappointed that it gave a very similar result as the GRMHD, I guess the ones I presume the even EHT team is using. And then of course there's the fancier option of using PIC and PIC, GR PIC. So my question, I guess, for the community is, so if it's giving such similar results, what's the strategy for moving forward? And I know people are working on all these aspects. So just having made these 2 comments, I would like to now invite Richard. I don't know if any of this was addressed or any highlights from your session.
Thanks, Chung-Pei. And I would like to just briefly summarize in the parallel session on plasma physics. We touched on a number of different tools, such as simulations that had adaptive ray tracing, and we touched on a different model improvements, such as the inclusion of positrons, and we touched on a number of different potential observables that these things could affect, such as Faraday rotation measure. And I think that the main emergent takeaway is that the assumptions that we use in order to just generate papers in an analysis pipeline may not be the most general assumptions, or may not be an unbiased set of assumptions in order to analyze the system objectively and blindly. So we should keep in mind that historically we may be able to get one sort of general relativistic magnetodynamic pipeline working in one way, but then the cost of doing that, let's say that we forego resolutions so that potentially we don't see plasmoids forming in current sheets, or we forego positron content because we don't currently know how to incorporate that into our general relativistic magnetodynamic equations. Those costs need to eventually be reckoned with in order to really fully account for the effects, unless we quantify, and usually in practice, if we're just analytically quantifying the errors, it might be intractable, and it really may be just a stopgap between actually putting all these effects into the simulations. But it's an absolutely fantastic achievement that we've been able to put together reconstructions of black hole shadows and the surrounding accretion flows. But it's another matter that may have to be checked sooner than later. What are the needs to explore different effects of the particulars of the initial conditions of the simulations, the methodologies that the simulations are using in order to produce radiation, the specifics of the radiation physics, and computational advances like GPU acceleration may prove an avenue. But maybe it's good to start and just systematically lay down the questions, maybe make the Hilbert problems of GRMHD plus black hole imaging, and just lay out what are the most general approaches to exploring the systems that we have, not just the ones that are based on the current tools that we have. And also, with that said, I also want to make some mention of and it could be that the dichotomy between the simulations that Elliot was showing that weren't able to come up with jets versus the simulations that Sasha was showing that readily produce jets are just exemplary of studying the same system but having completely different phenomenology based on the different assumptions that are being used. And a lot of the ways that we can start to probe some of these degeneracies could be with different channels. So EHT, we're good at observing total intensity and 230 gigahertz plus a few hundred, but there are polarimetric signals, there are multi-wavelength signals, there are potential signals from gravitational waves, there are potential signals in particle physics due to all sorts of couplings that can occur in the Kerr metric with strong gravitational fields and with the hot accreting plasma that could be the key to breaking degeneracies that we see at the level of EHT images. So it may be worth also trying to come up with an exhaustive set of tests from other methodologies, other instruments, and we're doing that. We have multi-wavelength work that's coming out, and we do have a strong gravitational physics working group. But again, it may be just a good thing to step back from the drive for the most immediate results and to see the landscape holistically, to see how can we better and more efficiently make the results that we've been getting more robust. So that's my basic spiel.
Thank you. Yeah, thank you. Oh, welcome. So please raise your hands if you want to follow up or you have questions.
And I think there are other parallel sessions, by the way. There were 3, so I don't know if there are other summaries or.
I don't know, are there questions in the Slack channel? Thoughts? Michael, go ahead.
Yeah, kind of going back to what you what you said about the cosmological simulations, I think that's a really interesting parallel. And I think a lot of the GRMHT work has been done in these kind of one-off exploratory directions. So the EHT has kind of made this library, and we heard about the hammer simulations. Sasha had a quote, I forget what I think it was, "Science is no longer computationally limited," which I thought was pretty bold. But I was just curious, how close are we to really more representative simulations, especially with more complex boundary conditions for the accretion flow? Is that a priority among, I don't know if Sean's on the call or I see Andrew's here. Where does that lie on the priorities of the people running these simulations?
Yeah, I also see Jim Stone here. So any comments from the experts? Okay, go ahead, George.
Speak for Charles, who apparently is not currently not in this meeting. I know that we believe, for a variety of reasons, that it will be very important to look at, for example, these wrestler simulations of infall with the more realistic boundary conditions, as you say. Imaging them and exploring different models. I think that there are a variety of reasons why the current library, extensive as it is not sufficient. It doesn't span enough parameters to accurately account for all the things. So I think that that's very important, and it's something that we're looking into actively.
Okay, thank you. Avery?
Yeah, so along those lines, I think Sasha underestimates the creativeness of those of us who wish to abuse large computing machines. We can always find more interesting things to do. And George, you bring up a really important point, and that is, as we look towards a glorious future with massive development on the instrumental side and a new, much more filled in and powerful array, we will need to match that with development of ever larger computational resources and suites of simulations that can involve a great deal more physics than's been included now. So we saw from this week already, Elliott go all the way from the surrounding disk of stars, which presumably feed the accretion of the Sagittarius star, to the horizon. Those kinds of multi-scale simulations will become ever more important. We also saw from Sasha and Bart these extraordinarily high resolution simulations in which the character of the accretion flow seems to be somewhat different than what it looks like in the lower resolution simulations. And I wonder how significant that transition is going to be. Is that going to produce changes in kind for these accretion flows? Or is it really just coming up with beautiful ultra high resolution computational art? And that's a question that has to be answered in addition to things like evolving electron distributions, dealing with long mean free paths and filling jets potentially with different populations, et cetera. But maybe that question would be for the simulators. Does this ultra high resolution simulation stuff lead to differences in kind? Are we going to have to redo all of the simulation endeavor with 40,000 grid cells to a side?
If I may comment on what Avery said, I think the kind of simulation that Sasha and I showed is one that we can only do one of them, sort of. It's too expensive. We can do one per year if we're lucky to get the computing time. So I don't see how this could sort of replace a full EHT library. I think how we should see it is that we can learn a lot from these high resolution or converged simulations, and equally much from simulations that include more physics than we generally include. And that can sort of guide us in how far we can trust the fiducial simulations. I don't think you need such a high resolution simulation for every spin, for example. I think you can learn a lot from a single one, or maybe two representative spins. And then you can draw conclusions. Like if you look at the high resolution thing that showed plasmoids, I think it looks a lot of the time it looks like a standard mat as we know it, but just there is a short like period where a current sheet forms transiently, and it's like non-axis symmetric. So at that point it looks completely different than a standard simulation. But that's only like a temporary state that might cause a flare, for example. So if we're after the flare dynamics, then I would say it's essential to run a simulation like this. But if we're after an EHT image, it might or it might not make a lot of difference. But we can check that with one single simulation or like one range of resolution simulation where we compare images, and then we can say a little bit better whether we're in trouble with the EHT or not. So I would say there are definitely differences, but we don't need to throw out the whole library.
Thank you. Just time-wise, I want to say, let's combine the plasma and the shadow, since it's a similar conversation, and also the chair of the shadow session can't be here. So I welcome more comments, but then I want to leave the last 10 minutes for the time domain discussion. Okay, so please go on, Razi.
Yeah, thank you so much. That was very excellent discussion so far. I was wondering, is there any chances that in the real time we can replace all of this sort of simulation with something like machine learning, in which instead of just like, requirement to do and just like run off each of them for half of a year or so, you can just actually have a pool of them that can be understood, or just like run, not even like a run, just like actually be formed out of the lessons that we have out of these individual runs, or we are very, very far from that side now?
My guess is very far, but anyone would want to comment on that?
And what caused it to be that far? Because, there are many details that in a real time we may not even notice actually. So you see my point, like, is there any possibility that we could just like gather all of this information such that you can just get very actually good way of probing them without necessity to spend years and years of more simulation, or not?
So I think that machine learning will be a large part of the future, but I think that, so there are of course different ways you could apply machine learning. One would be to generate the fluid simulations, and another one would be to generate images. And so we've looked at kind of the opposite problem of, can you classify images with machine learning? And so, we've generated suites of tens of millions of images and run machine learning on it. Obviously machine learning works for classifying images for the parameters that we've specified. But once you start to deviate away from those parameters, so different electron distribution functions and so on, it seems to break catastrophically. So maybe catastrophically is too harsh. But I think that kind of you would run up against the same problem. So you have the problem of, you need to span an appropriate space, and you need to span it first, and then you need to use that as input to train the machine learning networks. So it's kind of just begging the question. That's my perspective.
Yeah, so at least in the galaxy formation and cosmology worlds, we're absolutely moving towards the machine learning world, but you really need to have a huge library of things to learn from before you can do it. But each individual calculation here is so expensive. That's my guess, is it may just take a little while longer to gather the information. Yeah. Okay, so I see Andrew.
Yeah, I just want to make a brief comment. I think maybe the time has passed, but just that, as these simulations become more capable and we're able to do higher and higher resolution things and incorporate different physics, I think that's somewhat at odds. Like, it's a different direction, a different tension that's pulling us in a different direction than our desire to maybe like sample parameter spaces more fully. And I think it's good if we try to, as a community, work together as much as possible on determining, what are our highest priorities and simulations that we need for the ngEHT and for other purposes. I know from experience that once we run a simulation, we start mining it for years for, different physics, and we've already started seeing that with the EHT simulation library. So I think it's just often these decisions are made by individual groups, and you make a decision maybe for personal reasons or some element of arbitrariness, and then that ends up getting propagated for a long time. So I think we have a chance as we consider the next generation of simulations to really think carefully about, what the spaces we want to explore are, and what the different physics we want to include is. And I think it'd be great if we could do that sort of as a whole community, because we'll be probably setting the stage for years of work with whatever simulations we start running.
Thank you. Yeah. Okay, so maybe the last question on this topic, Shep.
Okay, well, I suppose I have a question that combines a number of things: time domain, shadows, and maybe even plasma physics. But there was a talk in the shadows section about rings formed by the jet bases. So you could get a ring that was not produced by the photon orbit. And there you might be able to tell the difference between them based on time variability. So I'm always interested in what can masquerade as the photon orbit, because those are very dangerous if you want to make tests of GR. And so I want to know what people think about this. My approach to this would be to use an operational mode of the ngEHT that could sample things in such a way that you would tease out the differences between these kinds of rings based on their astrophysical genesis. So for the photon ring, there'd be one time constant, but for a lensed ring due to a jet base, that would be something else. And so if people have some ideas about that and they could put them into constraints on operational modes for the ngEHT, that would be most helpful.
Thank you. Sounds great. And this may be a good time to pass this on to Alex. I don't know if they have any discussions.
Oh yeah, thanks, Chung-Pei. So kind of following up on what we've been talking about, we need to, match the development of an ngEHT array with the development of these computational simulations. But I think from our session, we kind of got two main points that came out was we also need to match this development of an ngEHT array with supporting multi-wavelength observations, as well as new analysis techniques to extract more information from the data. So for one, we heard a great talk from Daryl telling us all about how the multi-wavelength is really important in complementing EHT efforts. We have all these different probes from multi-wavelength, whether it's like rotation measures, polarization, SEDs, flares, that really kind of help us understand accretion flow parameters like temperature, density profiles, and the like, as you kind of move inwards to the horizon scales. So multi-wavelength is really important in kind of putting into context what we see with the ngEHT kind of data. And then number two was we heard a lot about some really super cool new techniques to extract more information from EHT data, in particular with the time domain. By just considering a static image, you're really throwing away a lot of information. And we saw from a lot of different talks that even we can extract really kind of precise measurements actually of accretion flow parameters and understand the origin of flares from even using the simplest models up to the more complex kind of full GRMHD models. So I think there's been kind of a lot of talk since day one of the meeting that we kind of want to define what new observables that we can get out of data from an ngEHT array. And I think there's a lot of new things that we can do, in particular with the time domain. So I'll kind of follow up on what Shep was just saying and kind of point to the speakers in my session. So Daryl, Roman, Paul, Kataro, Shahar, and what kind of capabilities would you think would be most useful for the ngEHT that would really help us take advantage of all these new techniques that you guys told us about? Yeah.
Any thoughts along this line? And I don't know if there's any, there must be some plan for further discussion on Friday also.
I mean, well, at least for what I was talking about correlations, autocorrelations, I think an advantage of that method is that you do not need to resolve really fine features in the image, but you actually do need to average over a long time. So actually more telescopes is a good thing, and more time on the telescope would be good. But yeah, so I mean, this is something that can you don't need to go to space for, but but it would be it would significantly benefit from averaging time.
Avery?
So I've heard averaging invoked a few times, and as somebody who plays with a lot of data, I do enjoy synthesizing answers to simple questions from complex data sets, which is just averaging. But I would just caution people that averaging images is very different from averaging the observed complex visibilities, because you don't necessarily have a way to coherently phase the visibilities. So clever ways to deal with observational issues, be it some technological way to address the overall phase fluctuations, maybe phase referencing observations, or in the analysis. So come up with ways to incoherently average the visibilities and still get the science out is going to become increasingly critical. So I would just caution people when they think about these questions of, well, I'm just going to average down all the fluctuations in my image and get something that's pristine. That's not really how it's going to happen. And we ought to think about if we can be optimal.
Michael?
I guess two things. One is Chung-Pei, you mentioned about day 5, and indeed day 5 is going to be just breakout discussions where we really try to go through all these different ideas and see what's possible and what's necessary to explore different sources and so forth. On averaging, I mean, I think it's tremendously underexplored. I think there are ways that we could tailor the architecture of the instrument to allow coherent averaging. So instead of our current limit is 30 seconds, maybe that could be 6 months or something, right? Because the errors are station-based. So as long as we have short baselines, then you can phase reference to maybe stable image features, and then you can transfer that coherence to long baselines. But I just think maybe there are parallels in other types of VLBI, but I just think there's a lot of progress we could do on the technique side and push towards things. So I wouldn't be so pessimistic. I mean, I just think if you can establish that a requirement to measure something is 6 months or 2 years of averaging, or something that seems absurd, that's fine. Then we can start to see, is there any way to tailor the instrument to allow that? And I think we might be surprised.
Andre?
Well, yeah, I think it depends on the nature of the question that you're answering. If you know that you're well, the question is like you want to get the scale of your ring, which is supposed to stay constant, then you can do the averaging. Say that you need to do coherent averaging in order to get detection. After you've detected the emission and you answer such a fundamental question that an actually answer to that is not changing on certain time scales, then you can do the averaging without harming yourself, because you'll be getting all the answers from that wavy pattern. The amplitudes will change, but the dips and peaks will stay in the same place, and then the answer will then be the same. You measure the size of that ring and measure its width. That's what you're aiming at. If you're aiming at something more complicated, like getting the decent image of Saj star, of course, it's a different story then. That's I can see there are two phases of averaging. The coherent averaging, you need to do it for detecting things. The rest depends on the nature of the question. You can average them as long as your question allows you to.
Thank you. Lindy, you have a question? I know we have about 1 minute left.
Just a brief comment on the averaging. Avery, I wasn't sure if you were talking about averaging over sort of astrophysical variations, or if you're talking about averaging over systematics because of detectability. But generally, if you have a complete model, you don't need to do incoherent averaging at all, which is really nice about the modeling frameworks. And I guess the last thing, I also had something to say in response to Shep's comments. Autocorrelations were brought up, and it was also hinted at during the session, which is that there were spatial self-similarities between these different rings. And I think those also have a lot of utility during model fitting, which I'd like to see used in future analyses. I know people are working on this.
Okay, thank you. I think we have a session scheduled for 1 o'clock, or sorry, I'm in Pacific time. What time are you guys in? 4 p.m. Eastern? Yeah, so great. I think we've raised as many questions as we've answered, and we've touched on both simulations and data analysis and so on. I think this sets up a great stage for further discussion on Friday and probably discussions tomorrow. So again, I want to thank the moderators from previous sessions and all the speakers, and thank you for your participation now. So I think I'll give the hand this back to the LOC